Welcome to Spring LIB.
Hello everyone, thanks for joining me today. What we're going to be looking at is an application of Newton's second law, and we're going to be looking at the concept of friction. So what we have is a man who is moving a box. We know the mass of the man is 75 kilograms and the mass of the box is 150 kilograms. We know the static and kinetic frictions between the box and the surface to be 0.3 and 0.2 respectively, and we know the coefficient of static friction between the man's shoes and the ground is 0.8. What we're asked to solve for is to show that the man can move the crate and also the maximum acceleration the man can give the crate. So as I stated before, we're going to be using concepts of Newton's second law, which will include us drawing free body diagrams and using F equals ma. So let's go ahead and get started. So what we're going to do is we're going to first assume that the crate is about to slide. So what we can do is apply Newton's second law and say that the net force in the y direction is equal to 0. Knowing this, let's go ahead and draw the free body diagram of our box. So there's our box. We have a weight force acting down on the box. We have the normal force acting from the ground in the vertical direction. We have the force that's applied by the man, and we have friction, which is opposing the direction of motion. Next, what we can do is look in the y direction, and we can see that the only two forces we have acting in the y direction are our normal forces and the weight force. Therefore, we can say the normal force minus the weight force is equal to 0. Then we know that the normal force is equal to the weight, which we know is just going to be the mass times gravity of the box. So this gives us a normal force that's equal to 1,472 newtons. Next, we can do the same Newton's second law in the x direction, so let's go ahead and do that. We can say that the net force in the x direction is also equal to 0, since we're assuming the box is just about to move. Therefore, we can use our static friction and say that the static friction times the normal force minus F, which are the two forces acting in the x direction, as shown here, are going to be equal to 0. Therefore, what we can say is that our F is going to be equal to mu s times the normal force, C. And we can say that our total force provided by the man is equal to 441.45 newtons. Using these pieces of information, what we can do now is apply those same Newton's second law on the man. So drawing the free body diagram of the man, here's the man pushing this box, and he's on the ground. We know the man has a weight force that is pointing down. We also know the man has a normal force from the ground. We know the box is pushing back with the force of F, and we also have friction going in this direction. Call that FF. So what we can do now is apply Newton's second law in the y direction and say that the net force in the y direction is equal to 0 because the man is not accelerating in the y direction. Therefore, we know that the normal force is equal to the weight force, which is equal to 736 newtons. We know this because we know the mass of the man to be 75 kilograms, multiply that by gravity, and we can get this normal force. Next, we can do the net force balance in the x direction and say that F minus FF is also equal to 0. We can solve for FF and say that FF is equal to F, which we know to be equal to 441.45 newtons. Next, what we can do is we can say that the total possible maximum static friction force is going to be equal to mu s between the man and the ground, so let's call that us prime, times the normal force m. And we know that this is equal to 0.8 times 735.75, which is equal to a maximum static friction force of equal to 588.6 newtons. This value, which we will just call mu s prime nm, is greater than the friction force that is required to keep the man moving the crate. So what that means is that FF is less than mu s prime and m. Therefore, we can say that the man can move the crate. Man can move crate. Remember that we're also asked to solve for the maximum acceleration that can be experienced by the crate. So we know that the maximum force that can be applied by the man to ensure that he can move the crate is 588.6 newtons. So redrawing our free body diagram of the crate, we can say that the crate has a weight force, W, a normal force, the force applied by the man, but the maximum force that's applied, and we also have the static friction force, which we'll call Fs. So again, doing our net force balance in y, we can say that the net force in y is equal to 0. Therefore, the normal force is equal to the weight force, which will be equal to 1,472 newtons. Next, what we can do is we can say that the net force in x is equal to max. This is because the net force in x is not equal since the box is accelerating. Therefore, what we can do is we can say that the force maximum minus the static friction force is equal to mass times acceleration. We know that F max is equal to 588.6 newtons. And we can directly compute our static friction force by saying that this is going to be equal to mu k times the normal force, which is equal to 294.3 newtons. Then what we can do is we can directly solve for AX in this equation and say that this will be equal to 588.6 newtons minus 294.3 newtons divided by the mass of the box, which we know to be 150 kg. And this gives us a maximum acceleration of 1.962 meters per second squared, and that's our final answer.